Today we're going to be talking about energy bar graphs as a continuation in Unit 5, and hopefully those energy storage modes have been reinforced so now that we can move along and do something with them. Starting off, we want to discuss the two types of systems. We first talk about open systems and closed systems. On your note helper, we'll define an open system as a system in which energy cannot transfer between the system and the surroundings. For every scenario, we'll be able to define the system, and then we'll just define the surroundings as everything that we are not paying attention to in that particular scenario. In a closed system, since energy can't move in and out, total energy is therefore constant. There may be changes between storage modes, but the total quantity of energy contained within the system stays the same. In an open system, energy is able to flow between the system and its surroundings. And although open systems may seem like energy has been gained or lost, it's typically due to some type of energy transfer that came in or out. So we'll discuss in the next box the different transfer mechanisms by which energy can enter or exit the system. Before we move on, I wanted to show you two diagrams. The first one is an animation of a hanging mass on a spring, and you'll notice that that final bar over to the right hand side in green has the label sigma E. Sigma stands for total, E in this case stands for energy. So you'll notice that that green bar doesn't change. The total energy contained within this system stays constant. Therefore, it must be a closed system. But what you will see is that there are different shifts or transformations between energy storage modes. When that spring is at its highest height, you'll notice that GPE bar is totally to the top. All the energy in the system is stored as GPE when that's at its highest height. As it starts to fall downward, you'll see that the GPE decreases, but with an apparent loss in GPE, you get an increase in the elastic potential, that's the gray bar, or energy stored within the spring, and you also get an increase in kinetic energy. That's the energy of motion as that mass picks up speed. On the next diagram, we'll notice an open system, and we can tell it's an open system because there, at the end, that total energy bar goes all the way down, indicating that energy has left the system and been transferred out. In this case, we can probably assume the energy gets transferred into the wall. You'll notice that on a roller coaster, which is a very popular theme with energy transfer within a system, you'll notice that as the roller coaster has different speed and different heights, that GPE and KE will shift. But at any moment in time, if we were to pause and look at the height of the blue GPE bar and the, what color is this? I don't know, gray, black KE bar, if we were to stack those on top of each other at any moment in time, it would still equal the total energy bar of the system. We'll let that replay once more. Okay, we'll let the roller coaster play one more time. Sorry, the recycling people interrupted us. And then we'll move on. Okay, speaking of an open system like such, if energy were going to enter or exit a system, it would do so by one of the following four transfer mechanisms. Go ahead on your note helper and indicate that in would have a positive sign, out would have a negative sign as you expect, and the first transfer mechanism would be massing with the symbol capital M. Examples of energy entering or exiting a system via massing would be eating, sweating, that would be the loss of water, which has mass, any excrement, hopefully every day, you mass in and mass out properly, all ways to transfer energy into a system. The second energy transfer mechanism shall be, this is the bottom left-hand corner, radiating, symbol R, and that can occur with light or sound being emanated or given off. Third transfer mechanism has an equation attached to it, which we will use at a later date. Energy can enter the system by work being done on the system, that'd be positive W, or the system doing work on another object, that would be negative W. It essentially comes from some force that's applied over some amount of distance, energy being used to do work, in or out. And the last transfer mechanism would be heating, symbol capital letter Q. If the system takes in heat, that's a way of inputting energy. Or if the system gives off heat, that's a way of energy exiting the system. Okay, so as we look at this animation, I need to click play here. You'll notice that there will be two depictions of energy transfers. One is with this circle graph here, which we tend not to use very much anymore. And the other one is over on the right-hand side here with these bar graphs. They're labeled kinetic energy, potential for this simulation. They're really talking about GPE. Thermal energy would be our dissipated energy, and the total is the last bar here. Green, chartreuse, whatever color that is. So what you'll notice is that here starting, all the energy is stored as GPE due to the person's height off the ground. This, I have it set where this is not a closed system. You guys will be able to do the same simulation later, and we'll have some other settings with it. But since it's not a closed system, you should expect for this green total energy bar not to stay constant. You should expect for some of that energy to leave or be dissipated, transferred out of the system due to heat in this case. It's the friction of the skater going up and down the ramp. So here I'll set it into motion. And there he goes. The reason why he can't make it up to the same height each time is because that energy is leaving the system or being dissipated each time he goes back and forth. We'll notice that at the end, he does still have some GPE left just because of how this track was set up. It's off the ground. So even if he's not in motion or not at the highest height, he'll still have some GPE just because of how the track is arranged. Okay, so for our bar graphs, your setup will look like this. They are used to represent how energy is stored and transformed, within a system. Essentially, the most basic setup of a bar graph will have the initial bar graph on the left, and then we may have different points of energy storage in between, but if we don't choose to break it down into several different points, you'll have the final on the right. We'll start off with just an initial and a final scenario, and then as we move to the back of your note helper, we'll have bar graphs with several positions in between the beginning and end. Okay. Your first scenario is as follows. If we want to make a bar graph for a ball that's held at rest 1 meter above the ground, that is our initial scenario. If I can take a pen, what I like to do is I like to block off with the pen. I like to block off the initial scenario and the final scenario like so. So here's the initial scenario, bam, from the beginning to there. And then the final will be, it's then released and has fallen how far? Halfway to the ground. Yeah, that pen is hard to write with on here, but okay. All right, so if I can bring up the bars for each beginning and end scenario. In the beginning, if it's held at rest above the ground, it's not moving, therefore you will not have any KE. There's no elastic component here, and the dissipated, none. So we can indicate that your bar is all the way to the top, full GPE. Now you may be wondering like where we get these numbers or amounts from. Bar graphs are a very general way to show energy storage at different moments in a scenario. So what we want to focus on is that from beginning to end, if this is a closed system, like it says up here, we're starting off with the easy ones, that if you have 4 bars in the beginning, you need to have 4 bars present in the end because energy cannot be created or destroyed. It can only change form. The total quantity shall remain the same. So the final bar graph happens like this. It's released, and since it's fallen halfway to the ground, if you lose half your height, you should expect to lose half of your GPE. Sketch that in. And since the GPE has decreased, that must mean that in this closed system, something else increased. As expected, falling objects, they do decrease height, but as they fall, they will increase speed. So there is the rest of your energy. The initial total energy does indeed equal the final total energy in this closed system. So there's your first bar graph. Turn the page. Now you have Another scenario, a load of bricks is resting on a compressed spring. Since you're talking about a spring, you will definitely have elastic potential, but since these bricks have some height off the ground, we'll give it, say, half a bar of GPE. The remainder of the energy to make the system total 4 shall be, the rest of it is elastic potential. Now in the final scenario, the words indicate that the bricks have just launched into the air and just begun moving upward. So now the spring has sprung and there is no longer energy stored within the spring. So since it's popped open, now it's a little bit higher off the ground. So we'll increase the GPE to say 1 bar. And where does the other energy go to? Energy of motion. That would be kinetic energy. If we total up from the initial to the final scenarios, you still have the total quantity of energy remaining consistent. Storage modes have changed, but total quantity of energy remains the same. That's the law of conservation of energy. Scenario number 3. Here's where we can talk about different bar graphs for points in between, not just initial point A and final point B. So let's go through. The top row is A position, B position, and then the bottom row shall be C, D, and E. If you want to pause the lecture at this time to try to fill these in on your own, that may be a good idea, or you can do it with me. At A, it's definitely not on the ground, so we have slight GPE. 1 bar should be sufficient. Since it has started moving, whoever tossed this up, you'll have kinetic energy, and it's at its fastest when it first leaves the person's hand. As it travels higher, now we're on position B, the GPE has definitely increased from 1 bar to say 3 bars, and the speed has decreased. So there you have it. And at point C, essentially there is no motion. GPE is at its full quantity, KE is none. As you start to come back down, since position D is exactly halfway between the origin and its highest height, you'll have half GPE and half KE. And position E should mirror identically position A. There's a knock at the door. Hold on. Sorry, we keep getting interrupted. That was our fish tank helper. Okay, example number 4. An egg is held at rest above the ground, then it falls and breaks. So initially, we have all GPE, all the energy stored due to its height. Once it falls and breaks, we're now doing open systems. Your final bar graph will have no energy left in the system. Why? Because energy has been transferred out. Go ahead and draw that in the middle via work, minus W. You probably will have also some energy transferred out via radiating because of the sound made, and so on. So we'll put those labels up and let you fill in the final as dissipated. Whenever energy is transferred out, we shall call it dissipated energy and label how. And last but not least, the super ball. Go ahead and pause and attempt to fill those in. This is again an open system, hence the ball doesn't make it up to its highest height for each consecutive bounce. Some of the energy with every collision on the ground is lost or dissipated due to that deformation and friction with the impact. A, total GPE. Here's B, elastic potential because the ball is being compressed, but you also have some dissipated. C, lower height, and dissipated is still the same. D, another impact, so the energy gets stored within the ball due to the compressing of the bouncy ball, and dissipated a little bit more. And finally, letter E, now it's back up to a height, but it could not achieve the highest height is letter A because some of the energy has left or dissipated. Your 15-minute flip notes are up, and we're just in the nick of time. See you on Monday. Please bring your note helper ready to turn in.